Good afternoon to everyone. Let's wait 5 minutes for all the people to attend. There were a lot of people registered. Good afternoon. As I told you earlier, this third webinar will be about junctions and how the 1, 2, 3, 5, 4 model these junctions and how do we deal with them in SONarchitect ISO. This time our research and development manager Alfonso Rodriguez is giving you this lecture. So he will explain how the junctions are modeled in the 1, 2, 3, 5, 4, and then how to proceed with modeling them in SONarchitect. In the very first webinar, I was telling you that you don't need to think that much because SONarchitect now knows the geometry of your building and also the material that you have assigned. So these are the parameters needed for you to model the junctions according to those KAJ parameters. Hello to the new attendants. I think we can start right now. I'm just proud to introduce you to Alfonso Rodriguez, and he will start with the presentation.
Okay, thank you, Castor. Hello, everybody. This is Alfonso Rodriguez talking. I'm, as Castor said, I'm the technical director of Sound of Numbers, and I'm also the responsible for most of the coding and programming behind the SONarchitect ISO. So I have been told by Castor that there were quite a lot of questions and suggestions about junctions, and I will be happy to address those questions along this lecture. Most of them I will answer them just through this presentation that I'm about to give you, and after that we will have some time just to maybe address a particular question from customers and well, any kind of questions. So in the next few minutes, I will introduce you the basic concepts of how the junctions are dealt in the ISO 12354. So you get the very basic concepts of how this model based on statistical energy analysis deal with vibration reduction indexes, and after that, here, okay, okay, coming back. Good. And after that, we will get into details about how we implemented this model in the international standard inside SONarchitect, and then how this programming has improved the way that we deal with the model. So let's start right now. This is a very basic outline that I will talk in during these few minutes. I will introduce the concept of planking transmission through the model in ISO 12354. Then we will review the formulas in the Appendix E of the standard, where is the source of all the information needed to implement this model. Then we will see how the junctions are implemented in SONarchitect, and then we will go to some points, some interesting points for most of the people that are how the double heavy walls are treated, because there is not too much information in the standard for the moment. And then we will talk about approximations. How can we approximate cases that are not inside the formulas in the Appendix E? And then maybe we can just discuss a little bit about future developments and a few conclusions. Okay. Okay, I want to go forward. Yeah. So maybe you are already used to concepts about statistical energy analysis. It's not the aim of this lecture just to give a deep introduction to statistical energy analysis, but just to take a little bit of background of the context of the problem. Maybe you should know that the basic idea in the ISO 12354 treatment of vibration reduction indexes is just to change the way that we calculate the vibration, the Planck transmission to mechanical elements from the coupling loss factors to the KAJ indexes. And this is basically made through the model that Eddie Gerritsen presented a few years ago, more than 20 years ago. And this very model was very important for the development of for making a new way of calculating sun insolation in buildings, because we changed a value that was very difficult to obtain in reality, which was the coupling loss factor, to something more similar to what we can measure in a laboratory, or we can get in real scenarios. So, and this is the innovative point of the Gerritsen method, that was to transform this coupling loss factor to another shape of them that were called by him the vibration reduction indexes, also known by the letters KAG indexes. So Appendix E of the ISO 12354 provides a set of KAG indexes covering what can be said to be the most common configuration in building. However, it's very easy just to go out of those limits, because the way that the buildings are built in Europe are very different from north to south, or from if we use some particular element from the new development, or even through the time. I mean the way that we built buildings 20 years ago ago were very different from how do we build today. So the problem is that the KAJ indexes are still the same, and it is not growing. I mean, at least not from the end of the ISO 12354. There are some researchers that are working on new models and for making the prediction more accurate. But the fact is that we still have the same KJ indexes and in the standard. And in order to make to calculate for new models or models outside this Appendix E, we have to go to research. I mean to articles in journals and things like that. Okay, there's another important thing to know about the KJ indexes in the Appendix A, that this is that they are not accurate. I mean, they are just approximations that have been agreed between several institutions, between several laboratories and universities. So they measured the same sound reduction, the same vibration reduction index for the very same junction, and they found that there was quite a lot of variability. So yeah, they had to take the values that were safe for the calculation. So most of the KJ indexes that you will see in the Appendix E are lower than real values, and they were somewhat simplified just to make the calculation easier. So in fact, or at the end, what we have in this Appendix E are models, useful models for making calculations, but we still are at the beginning of this process of calculating the sound reduction index with reliability. So we still need the knowledge of the acoustic engineers to make this calculation trustful. So you will find a lot of cases that are not covered by this Appendix E, and you will have to find for new models or see how these models are behaving in reality, or making a comparison against measurements and the result of measurements in laboratory.
Yeah, let's say is it everything okay? Can all of you hear and listen clearly to Alfonso? Okay, great. So let's move on.
Okay.
Just to check. Thank you.
Oh. It would be funny to find that I've been talking just to the air for a few minutes. Okay. So I was just introducing this lecture. So let's have a view how those models in the Appendix E of the ISO 12354 are. So maybe you already know about this. Yeah. But basically, in order to calculate the reduction of the vibrating energy from one element to another element, the first thing that we need to make this calculation is to know the relation, the ratio between the masses per unit area of those elements. So here, this formula, which is the logarithmic ratio between two masses per unit area, where, for instance, if we want to calculate, can I draw here? Okay. Yeah. Okay. So let's say that this is the initial where our vibration is coming from. So here we have our vibration. So for us, this will be our A element, and then if we so in order to calculate this M element, this M value, we need to know that this ratio, it depends on where the vibration is coming through and where it's basically where it's coming through. So this will be the A element, the I element, sorry, and this one will be the perpendicular element. Okay, yeah. So this one will be the mass per unit area that we will put in this part of the formula, and this other one will be here. Okay, this is maybe a bit confusing at the beginning because you have always to change the ratio if we are calculating another Planckian vibration reduction index depending on where the vibration is coming from. Okay. If you know a little bit about the Appendix E, you will find that there are several types of junctions and several models that can be applied to different types of junctions. So depending on if you have a rigid junction or a junction with resilient interlayers, you will need to select a different model and applying it to calculate the vibration reduction index. So I have to change the okay. So the first model that you will see in the Appendix E will be the model for the rigid junctions. Also, there are in this type of junction, the rigid junction, you will find the cross junctions and then the T-junction. Basically, the model is made with these two equations that you can see in this slide. Each one of these expressions will mean a different vibration reduction index. So here we can see the vibration reduction index from 1 to 3. This is from element 1 to 3. This means the attenuation in the vibration energy that we can see from a vibrating energy going from 1 to 3. Okay, and this one, the key 1, 2, goes from 1 to 2. This is from here to here. Okay, so this is easy. We can also see that this K12 will be equal to K23. So it will be the same as that as going from here to here, and also from from 2 to 3. So what we have in these formulas is just this ratio that we have seen before, this M ratio. We have a linear dependency on this ratio of masses, and then a nonlinear relation, a squared M value that made these expressions to behave as we can see in the graphs in the bottom. So for in the case of the first expression, the K13, we can see that at the beginning, when M is low, we have a very low vibration reduction index, which means that we have a very few attenuation or a lot of vibration transmission from 1 to 3. And as we increase the difference between the masses and increase the ratio between the masses, we have an increase in the vibration reduction index. For the case of the K12, it's not that much. We have something that is more or less more steady depending on the ratio of masses. The situation is very similar for the T-junctions. In this case, the formula also depends linearly on the M and in the squared value of M. But however, the coefficients are somewhat different. Before we have a 17 and 8.7, and here we changed to 5.7 and 14. But the behavior is more or less the same. We still have a K13 going from very low values for ratios below 1 to great values for ratios for higher ratios of masses. Okay, then we go to another completely different model, which are those junctions where we can find an elastic interlayer between the elements. So I will not get into detail into this because it will be quite a lot of time, and maybe we can go to more interesting stuff. But just I want just to remark that here we still have a linear dependency on M and also on squared value of M. But we can also find a new factor, which is delta 1, and this delta 1 will depend, and we can see here, will depend on frequency. So whilst before, for the rigid junctions, we found that the Kj will not depend on frequency. They are assumed to be constant for all frequency range. For these elastic junctions, we will find that the vibrational reduction index will increase with frequency, because this one is the frequency and this one is let's say a reference frequency, which is 125 hertz if a given relation is super. But the main idea that I want to remark in this model is that we will have a vibrational reduction index that will increase with frequency, and that in the case that for instance, in this vibrational reduction index K13, and will correspond to this Planck path, okay, that is going through 1 and 2 elastic interlayers. We will we find that we have here a value of 2. So while in the vibrational reduction index of K122, we find the Planck transmission goes just through 1 elastic interlayer. So we will have just the reduction of one of the layers. This is a very interesting fact because some researchers like Shoplock Paspan from Belgium have presented new models that try to model different behaviors of junctions that are not covered by the Appendix E, just through this approximation through delta 1 or similar quantities as delta 1. So that when we find an elastic interlayer through the Planck path, then we have an increase in the vibrational reduction. Yeah.
As usual, okay, I have some feedback from you and I like it. But as usual, since this is a very theoretical presentations, you can take note of your doubts and we can answer them at a Q&A session at the end of this presentation. Is it okay? Please don't get too bored, and so because the fun is at the end. Okay, let's move on.
Yeah. 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 So let's go on. There is another model which is called the lightweight facility junction. In this case, the model is quite simple. We have a linear relation with the ratio of masses, and then a relation with the absolute value of the ratio of masses for K to 1 to 2. So yeah, and by this way we have this. I'm going to take again PEM. Okay. and that's the reason why we have this relationship with this going like that, and this is the absolute value from 1 to 2. Okay. There is also another model specific for drywall, the junction between drywall and homogeneous heavy elements. Again, I will not like to go into detail because this is going to be very boring. But I want just to focus your attention through these two quantities, which are depending again on the frequency. But in this case, we have that for the case of the vibration reduction index from 1 to 3, the relation is negative, so we will find that the vibration reduction index goes down while the frequency goes up. And for the case of the K1, 1 to 2, the vibration reduction index increases with frequency. Okay, we will see these effects later on with SONarchitect. Okay, and there's another model also for junctions between drywalls, and again we can find those factors always in this case are negative. They decrease with frequency. And finally, there is a model for rigid corners and changes in the thicknesses, which depends only on the absolute value of the ratio of masses and the squared value of the ratio of masses. So these are the models that are included in the Appendix E of the ISO 12354. I know there are lots of models, a lot of specific junctions that are not covered by this model, but we could talk a little more about it later on. Okay, let's see how these models, how these junctions are implemented into SONarchitect. Maybe you are used to another software tools for calculating sound distribution, and in those programs you need to insert the information about which specific model you want to use for a very specific flanking transmission calculation, for the calculation of a given flanking path. Of course, this is useful in case that you want to get a very specific detail of a given flanking path, and also have some interesting things in order to make a comparison between one case and another case. But of course, this is not something that you like to do when you are trying to make the calculation of an entire building. I mean, with hundreds of rooms and thousands of calculation cases. So what we try to do when we designed SONarchitect was to make all the assumptions that we can do from the point of view of the firm ourselves. That is, there are a lot of information when you draw the building into SONarchitect. There are a lot of information that is already in the model. So you don't need to say SONarchitect. If a given junction is a T or a cross, or if you have to use the model for the junction between drywall and heavy wall, because SONarchitect already knows all that information. Instead of letting the user to confirm all those models manually, junction by junction, we decided to make a smart algorithm just to assign the correct model for each junction. So For instance, here we have a sample of possible junctions that you will find very often in real buildings. And as you can see, for us it's very simple just to say, okay, let's take a T model for this first junction. We have here T, and this is a corner, of course, and this is a cross, okay, no problem with that. But as soon as we have this small differences in the angles, then the thing is not so easy, and not for a computer. So this is where we put our knowledge, just in the geometrical, the computational geometry algorithm that works just behind SONarchitect to recognize the shape of the junctions and assign the correct model for each junction. But anyway, we could make an algorithm that deal with the entire building and solve all the assignments between junctions and models in just a few seconds and make possible the calculation of the ISO 123.4 in entire building. So this is really the innovative aspect of SONarchitect, that we could implement the ISO 123.4 into a model, into an algorithm that can deal with entire buildings in just a few seconds. So let's have a look on. Okay, yeah, I just forgetting. Of course, there is a smart algorithm to recognize the shape of junctions, but there is also some more information that we can use to make the correct association with the model. And the information that we can use is just the material. I mean, when you assign a material to a given element, you draw a ball and then assign a material. This material will be a heavy wool or a light wool or maybe a light facade or whatever. And in any case, this information is already in the model, so SONarchitect use it to assign the correct model to this specific junction. Here we have the screenshot of the form that we use to insert new data in SONarchitect. One of the things that the program asks you to insert is if the material is lightweight, can be considered to be lightweight or not. So with this information, we just know that in a specific junction where this material is going to be used, we have to select the model of connection between, it will depend, between dry wool, light wool, or between heavy wool and light wool. In this specific case, we are seeing now the screenshot of a form with the calculation result of a given flanking path. Just to say here, we have the sound reduction index of the flanking path, the RIA. And here we can see the sound reduction index of one of the elements. This is the source element. This dry wool will be the source element, which is marked here in blue. And the silver element is ceramic block. And here we have the sound reduction index of the dry wool, and here the sound reduction index of the ceramic brick wall. And here we can see the variation reduction index that has been selected automatically by SONarchitect. And you will see here that this behavior with frequency is exactly the same that we have seen before, which was decaying the area from 1 to 2, and then taking the combination of the combination between dry wool and heavy wool, and this linear dependency on the frequency, this is positive. Okay. Yeah. The same can be seen for the model of the drywall. You have keeping in mind the formula for the K123 from drywall to drywall, that the dependency was negative. And here we can see it again. Yeah. So this is just a very brief demonstration that you don't really have to give some information to an architect to make it to assign the correct model to calculate junctions. However, there are some information that is not already in the geometry or is not already in the definition of the materials. And this information is if there is or not a resilient interlayer between elements. And in order to do that, we develop, let's say, a schematic or a language to assign elastic junctions to walls and to slabs in the building model. So I will present here just the concepts of this language or this way of interface to insert elastic junctions in some projects. Here we can see a wall. This is a representation in this language, and we can see some arrows that are on top of the lines. This line here, the line in the middle, okay, I'll try to make it straight. Okay. This line in the middle is the wall that we are seeing here in the screen right now. So if we want to add a resilient interlayer on the right part of the wall, we just have to click on the arrow which is in the right part. Okay, and to do the same in the left part, we just click on the arrow on the left. And we still have two arrows, one on top and one on the bottom of the line, and of course they are meaning to resilient interlayer on the bottom of the wall and on top of the wall. Okay. And with this simple rationale, we made it possible to assign elastic interlayers in a big plan where we have a drawing with a lot of walls. You can assign it very quickly because it's just one click for elastic interlayer. And still we are missing one important elastic junction, which are the junctions in the floor, I mean between the slabs because of the dilatation the junctions or slits. Okay, and in order to assign those elastic junctions, there is another mode different from the previous one, where the triangles, the arrows that you can see, are not on top of the lines, but just facing the lines. Okay, and when you just click on one of the arrows, there is a top view of the slabs that you are defining. If you click on one arrow, you will have the slit or the elastic junction right in this arrow, and then you click in the other one, you will have another in the other side of the wall. And of course, if you do things like that in reality, you will need to insert some columns, otherwise you will get your slab on top of the right. Okay. There is still something that can be simplified just by the definition. One of the options that we made available for our clients is just to define a wall that is whose data has been measured on elastic bands, which is in some countries often used. When you select that option to say that this material has been made or measured on elastic bands, automatically you will find that whenever you assign this material to a wall, this wall will be defined with elastic layer on top and on the bottom of it. Okay. There is the new point, the next point of my presentation will be to talk about double hanging walls. Because as you may have noticed, in the Appendix E of the ISO 12354, there is no trace of double heavy walls. There is no model to apply to a double heavy wall. However, double heavy walls are used all over Europe. They are very used in Spain, but not also in Spain. So that was a gap that we were missing quite a lot in this Appendix E. And because of that, there were a lot of researchers that tackled the problem of how the double walls affect the vibration reduction indexes, and how can we calculate those indexes to make the calculations for 1, 2, 3, 4. The reality is that there is not a clear consensus yet about which model must be used for the KADA. However, there is a model, which is a model proposed by Nexen, and in our experience, this model is behaving very well with results from measurements. And we have decided to include this approach, this Nexen approach, inside SONarchitect. The very basic idea of the Nexen approach is just to use a statistical energy analysis approach or model to calculate the vibration transmission between the several elements the elements which are in a double wall. Just to say the basics, the main idea in the Nexen approach is, besides of considering the vibration reduction indexes between the elements in the junction, the vibration reduction index between one wall and one of the lips of the double heavy walls, and from one of the lips of the double heavy walls to the opposite lip of the double heavy walls, and then again to the other one. I was meaning when you are using the Nexen approach, you need to calculate this vibration reduction indexes or the vibrational difference level between these elements of sub-elements of the double heavy wall. But you also need to take into account the innovation in the Nexen approach of a value which is called the delta R, which is an improvement between the vibration difference level between one leaf of the wall to the other leaf. And this is basically computed as the difference between the sound reduction index of the double wall minus the sound reduction index of one of the leads that are composing this double wall. As I have said, we have implemented this model into SONarchitect. So whenever you assign a double heavy wall and face another double heavy wall, this model is applied automatically. Here we can see that the vibration reduction index, which is here, vibration reduction index, is not presenting the constant value, constant vibration reduction index that we would expect from a rigid T-junctions, but is presenting a value which depends on frequency. This is coming from this delta R improvement due to the double wall. However, you must be cautious with this model in medicine because you cannot always apply it. I mean, it can be dangerous, or you just say, okay, you have a double wall junction, let's apply the medicine approach. But then you will be making a mistake. So our smart geometry algorithm have to be we have to develop our geometrical algorithm just to take into account those cases. Here in this slide we see a few junctions that are where a double wall is being used. However, only in the first row we can apply the medicine approach. However, in the row which is in the bottom, we cannot apply it. Normally, I will let the audience to suggest why in the first one we can apply it and why not we cannot apply in the bottom row. I don't know if this is the...
Yeah, can all you hear us? Are you following us? We are asking which row can be modeled with the medicine approach and which one doesn't. Just for waking you up. Okay, I think you are following us. Indeed, the ones that you can model are the top ones. That's going on.
Well, you are seeing the solution right here. But the basic idea is that you can use the medicine approach whenever you have a whenever you have between one side to the other, from the source to the receiver, you have a cavity in the middle. Here you have a cavity, again here and then here. So in this case, the vibration needs to go from one leaf to the other, and in this case is where when we apply this delta R quantity. However, in the bottom row, besides of having regarding having a double wall, the flanking transmission does not pull the cavity. So we can go from the source to the receiver without going through the cavity. Here again from the source to the receiver, and here from the source to the receiver. So in reality, we cannot apply the medicine approach in the bottom row. Here we cannot apply the medicine approach, but just to take into account rigid junctions with the sound reduction index and the mass per unit area of the single leaf of the double walls. But fortunately, all these things are taken into account automatically by SONarchitect. For instance, here we have a case where we connect a slab to a double wall. So the source element is the slab, this one in blue, and goes up to the wall, which is a double-headed wall. And in this case, you will see that we don't have this the influence of the delta R of the double-headed wall, but we have a constant value which corresponds to the vibration reduction index of rigid T junctions. In fact, this case that we have here is exactly this one here. Well, it depends if it is on the top or on the bottom, but you will find that this is the bottom, the slab, and then it goes up to here. So we are not passing through a cavity, so the medicine approach cannot be used. Okay.
Someone is asking, shall we answer those questions right now? Let's say you have some
Okay, yeah. We have a question from Christian Simon from Gothenburg. He's saying, could you address the loss factor of heavy back and side walls as well? Did you follow Annex E or how? Yeah, indeed. You are asking about the Appendix C, which is one that must be used to calculate the variation, the structural variation time of the elements. Yes, I don't know if I have the equation later on, but the answer for your question is simply yes. In order to calculate the variation time, the structural variation time in C2, which is in the situation, we must follow the equation C.1, and then calculate the alpha sub k through the equation C.2, which we need. Maybe. Yeah, well, it's in Spanish, but basically we calculate the structural variation time through this equation, which is 6.1, and this equation that is based on the total loss factor of the element, which can be calculated with the internal loss factor, and then a factor depending on the frequency, the master unit area, and also the radiation coefficient, and then again on the critical frequency of the element, area of the element, and then a summatory of the length of each of the edges multiplied by alpha k factor. This alpha k factor in situ can be calculated through equation C.2, which depends on the vibration reduction index. I don't know if this answers your question.
Yeah, what about now? Can you hear us clear now? I tried to increase the volume.
Okay. Did I answer your question? Okay. Maybe I should continue. There's another. How do you differential between the left junctions in horizontal direction? Well, I don't understand that.
Maybe, Bob is asking, how do you differentiate between the left two junctions in horizontal direction? Could you please extend that question? We are moving on, but please type it.
He's talking about one of these junctions. Okay.
Yeah.
Which one? But I don't understand the question. How do you differentiate between the two junctions in horizontal direction? I mean, I don't really understand the question.
Anyway, if you want us to get deeper in some of the questions, you can contact us and we can have a little chat afterwards.
Well, maybe I understand. Do you think that they are the same, these junctions, if they are considered horizontally? But I have just put the source and the receiver in a specific place. And SONarchitect always considers the source and the receiver in different places. I mean, when you are calculating the vibration reduction indexes from one room to the room in the same floor, the source and the receiver will not be up and down, but from side to side. And then the medicine approach will be applied to this specific configuration. I mean, this example that I showed you was just for these specific positions of the source and the receiver. Okay. Maybe we can chat later on with Skype and solve any other questions regarding this medicine approach. Let's move on to the last part. Okay. To the last part of my presentation, which is talking about what can we do with real cases that are not standard. So, I already mentioned this, but the standard assumes that its receiving layer will behave, will have a meaning into our vibration reduction index by inserting a delta 1 factor that will increase the vibration reduction indexes with frequency. The very thing is that when you find two receiving layers, you will find double the attenuation. And this approach has been validated experimentally, and in some cases where you can find junctions that are not covered by the Appendix E, but still have this behavior or this configuration that you will find two or one receiving layer, the attenuation is just like that will increase by the same ratio. In fact, some authors, Charles Paspan, that I mentioned before, are developing new model based on this approach, just with different delta 1 values. So this is a thing that in the future, hopefully in the close future, we will see implemented in SONarchitect. Well, as I said, this approximation can be used to cover cases that are not inside the Appendix E. Let's see, for instance, this case, which is from a congress paper by Charles Paspan. Here we find two cases where the double heavy wall have been supported on elastic interlayer. And the difference between the left case and the right case is that in the left the cavity is not going through the slab, but in the right we are having this cavity that goes from one floor to one. And we still can deal, we can approximate these cases, which are not covered by the standard, but we can approximate them through the models in the standard. Some examples are those that can be seen in this slide. The first one is the regular case where we have a double heavy wall on a slab. But if we create a slit in the slab, we can do that simply by adding an elastic interlayer on both sides of the slabs. So, of course, this will not be the same, but it will behave as an interruption in the slab. So you will find that the results are most similar to some approximations to this planking path. If we insert elastic interlayers on top and the bottom of the walls, which is exactly the same case that we have seen before in the right part of the sprint, we will find that besides the interruption in the slab, we also have elastic layer going from the slab to the planking pad that goes up to the wall. And this can also be modeled through an elastic interlayer on top and bottom of the wall. And finally, a construction that is very usual in Spain and also in Italy. We have a lot of questions about this configuration, which is a wall, which is double heavy wall, which is supported directly on the slab, the coating floor, I mean. This can be modeled. We have made some measurements just to check this out. But it can be modeled through the model of elastic interlayer, which is just on top of it. So there's an interruption between the transmission between one floor and the other. Okay. Of course, these are just approximations. I mean, the problem is how do you deal with real building when you are not when the actual models are not available, not in the literature, not only nor in the standard. So these are approximations that have been used these last few years, having very good results, and we are confident of them. Okay. There are other models that have been developed, are being developed now. For instance, also some shallow span. We have seen recently a model taking into the columns and pillars of the building and how they affect to the vibration traction indexes. From Italy also there were study just to check how the KDA indexes of hollow bricks were, because maybe you know or not, in Spain you have a brick which is somewhat different from the Nordic countries, which is a whole brick, holes in it. So it's much lighter, but we have found that the vibration reduction indexes for the rigid junctions are not well. The model for the rigid junction do not work well with these hollow bricks. And we are founding new models for them, and they are still on discussion. We have already done some studies ourselves. As part of my PhD, I tried to find a way of calculating the vibration reduction indexes, not through measurement, but through numerical calculations, the finite element method. And well, I published some of these results in the paper and also in presented in the Congress of Edinburgh in Aeronautics 2009. And the results were promising, but still there is a lot of computational work to do just to find the predictions for the vibration reduction indexes. Here you can see the value that I predicted with the finite element method. And well, the first thing that you will see is that the vibration difference level is not as constant as the standard is making us believe. But you will have a lot of differences, one-third value in one-third of the bands. So most of the values that of the uncertainty that we can see in the one-third of the band value of Sunny solution predictions as per 1, 2, 3, 5, 4 are due to these variations in the vibration reduction indexes. And there is still a lot of work to do just to make this uncertainty reduce and to get more precise results. So well, thank you for your attention. This is the end of my long, boring presentation about junctions. Maybe we can now address some of the questions.
We can now go to the Q&A time. So one thing that I like to mention is after all these thought issues, that is the junction identification and junction modeling in the 1, 2, 3, 5, 4, okay, you might consider that it's easier for you to just to assign the precise model that you find in a list of models where you can find a T, a J, or a T or a cross or an elastic layer or not. But you have decided to do that after choosing two specific rooms into a huge building, thinking that you are choosing the worst one. But we advise you to be careful because it's very hard to choose the worst case in a building, especially if you are using elastic layers. There are a lot of counterexamples of some thoughts that you can find somehow the worst case is just following some rules, and that's not true. So that's why we have developed a tool where you can build the entire building and just put some hints where the elastic layers are, and enter the geometry, enter the materials, and SONarchitect chooses those models for you, and it actually also extracts the worst cases of these huge buildings that you're dealing with. Yeah, that's true. At the beginning of the development of SONarchitect, with the first test that we did, we found very interesting results because at the beginning, acoustic engineers, we had the idea that we have a very good idea of what will be the worst cases in the building. But it was very funny to find that the worst cases, there were a lot of cases that were very bad, but we still didn't thought about them. So when you do a real building with real geometries, with not rectangular angles, you will find that there are a lot of parameters that you are missing, and some of them will be very important in the calculation of the sound isolation. And you can do the test. I mean, just take one of the projects and try to put it in the SONarchitect and say, okay, the worst cases will be that will be your guess.
and you will find at the end that maybe you are taking some of those cases in your list of the work cases, but there are other cases that you are missing quite a lot.
Yeah,
Yeah,
okay,
the main
matter of this webinar has ended. Thank you all of you for your attendance, but we can answer some more questions. We have time, we have plenty of time. And it's Paul Pendler from Austria is asking what is about new with cross-laminated timber. I don't know if I can. I don't think I can understand that question. Could you please retype it or answer it again?
Maybe
Maybe it's not possible to compare with lightweight massive construction. But what do you want to compare? These models, the 12354, SONarchitect.
You must understand that what SONarchitect do is just calculate as per 12354 the standard, international standard. So we included all the models that are inside the standard, and we tried to get the more valuable models for consider those cases that are not covered by the standard. And of course, we are open to include the new models as for instance, the vibration reduction indexes for timber elements. We are very interested to learn about it and implement it into SONarchitect. But for the moment, the models that you have seen in this presentation are the only ones that we are taking into account in SONarchitect.
We know that there are some lags in the good construction of sound insulation. Hopefully in the next future we will have some more.
Yeah, indeed. I don't know if I'm missing some question.
Anyway, you just wrote down your questions and you can mail us. Actually, at the end of this webinar, you have a survey that you can fill with your questions so we can answer to you directly. Yeah, you can through our enemy platform, you can access to all of our recorded webinars. So thank you all of you for your attendance. Feel free to contact us if you have any other doubts. And I will mail you with the range of some new webinars if you want to, of course. Yeah, indeed. Actually, there are some quick and answer questions in the manual of SONarchitect in the help file. But we will collect some questions and we will report them to the website. That's a good idea. Thank you, Andrea. In the download section, you can download the user manual. Yeah. Okay, so we are closing now. Thank you all of you for your attendance. Yep, but in English, Gabriel. Great. We will mail you with the arrangement of the new webinars. Okay, let's close. Thank you. Bye bye.